Hello, this is your National Weather Service in New York office. We're going to do another one of these looks back at a previous weather event, in this case actually two previous weather events across the region. We did one with a winter weather event earlier this year, also some thunderstorms moving across the area earlier this year. So now what we're going to do is take a look at two hailstorms we've seen across the region recently, one in our county warning area, another one in Albany's area, and we're going to compare the two. They each produced large hail, but one produced hail much larger than the other. We're going to look at the tools we can use to distinguish between the two storms and why one produced larger hail than the other one did. So we've entitled this A Tale of Two Hailstorms. So here are two storms around the time that they produced these hail reports. The one on the left was in New London County, in our county warning area, produced hail up to the size of golf balls, at least reports of hail up to the size of golf balls, 1.75 inches in diameter. The data are actually from the Boston radar, KBOX, it was on May 25th. And then the storm on the right produced hail up to the size of 4 inches in diameter, so we're talking about grapefruit size hail. And this was in Albany's county warning area, and the radar was indeed Albany's radar, KENX. So the first thing you notice, well, to start actually, what we're looking at here is radar reflectivity. It's what we're most used to seeing on TV or the internet when we look at a radar image, when we think of a radar image. And in its most simple form, it's basically how much power is coming back to the radar. So it sends out a pulse, gets reflected off of precipitation, hail, rain, bugs, whatever you may have out there, and however much power comes back to the radar, we see these colors to represent that. So the greater the intensity of the color, then the more power the radar is receiving. So your first thought, at least, is, well, I see higher reflectivity actually on the left than I do on the right, but the storm on the right produced larger hail. How does that work? And there are other factors we need to take into consideration. It's not just how much power is coming back to the radar. Is there liquid on the hailstones? How many hailstones are there? What exactly is out there, the composition of the particles. And so what we want to do is look to where the hail is actually forming to really get a good idea of the size of hail that we're dealing with. To do that, first we want to take a look at a schematic, a cross-section we call it. It's basically a vertical slice of a generic hail-producing thunderstorm to see how it is that hail tends to form. So we would imagine the vertical slice in this direction on our storm on the left and in this direction on the storm on our right. So here's that cross-section. We see our updraft, our strong area of rising air, and this is what helps to support hail growth. Here's our region of hail that's forming, and it's this powerful upward moving air that can support and loft growing hailstones. How do they grow? Well, the updraft is actually bringing lots of liquid water up into the storm, and it's actually keeping this liquid water, these liquid drops, in liquid state, but at temperatures that are below freezing. We call it supercooled liquid water. And these hailstones, they start from small sizes. They could be one of those drops that happen to freeze. But then as they're traveling through the updraft, circulating in the updraft, they're running into those supercooled liquid drops that are being pumped upwards by the updraft fueling the thunderstorm. They collect them. Then they freeze a little bit more, get a little bit bigger. They continue the process, get a little bit bigger, until they're so heavy that the updraft can't sustain them anymore, and they fall out down to the ground. So intuitively, the stronger the updraft, generally the larger we can get the hailstone to grow. But there's some other considerations too. You want this updraft to be nice and broad and organized, in the sense that we want our hailstone to take a nice long trajectory through the updraft as it's moving around in the storm. Obviously, if it takes a smaller trajectory through the updraft, it won't have as much time in the updraft where the fuel is located for the storm, and so it won't be able to collect as much and grow as large. But if it takes a nice long trip through the updraft, it can collect more supercooled liquid water, and it could grow to larger and larger sizes. So let's go back to our two storms now. These, again, are reflectivity, but now we're looking much higher up in the storm. We're looking around 13,000 to 15,000 feet or so. But what we want to focus on is the temperature in the region for each of these two storms is around negative 13, 14, 15 degrees Celsius or so. And we call this part of the area, and going farther up into colder temperatures, the hail growth zone. This is where hailstones can really efficiently collect that supercooled liquid water and have them freeze, have the supercooled liquid water freeze on them and then continue to grow larger and larger. So we call this part of the hail growth zone. This is where we really want to focus for these two storms. So the first thing we see here is the magnitude of the reflectivity. Again, that power coming back to the radar. We don't really see any huge differences. The maximum reflectivity looks pretty similar on each, but notice in the case on the right, the giant hail case, 4-inch hail, we see kind of a much broader area of high reflectivity, and also this donut hole here over Amsterdam, indication of a very powerful, organized, broad updraft. Remember, those were some of the ingredients we wanted in the updraft to get really large hail. We see that's more evident actually on the right. Smaller, very small area relative to the storm on the right with the storm on the left. So check mark to the right side first off. And to keep things organized, we put an outline around where we have the highest reflectivity. So now we're going to go forward. First off, I'll show you the two hail, or the hail characteristics from the two storms. Here on the right, here's a picture of one of the approximately 4-inch size hailstones, and look at the structure of it. A lot of clear ice, these weird lobe structures. There's definitely a more interesting look to it, and also just the fact that it's large at 4 inches. Then on the left, here's the nearly golf ball size hailstones that formed, and the key here is they're much more spherical. You know, they're more uniform looking. They don't have all these weird lobe structures on them, and also you notice some of them are much more opaque too, not as clear. So some subtle clues to keep in mind. So now we move forward to a dual pole variable differential reflectivity. This is at the same level as we looked at with the last one. And what we want to notice here is on the left, our differential reflectivity in that area where we'd be looking for the growing hail is all pretty much close to zero. We're not seeing any really high values of ZDR or very noisy varying values of ZDR. And what that tells us is that it's a lot of frozen particles. We're not seeing much in the way of liquid water. Looking at ZDR aloft is nice to tell us where we have generally just frozen precipitation, or where maybe we see a little bit of liquid, or maybe where we see some ice crystals. But these values of close to zero throughout are telling us it's mostly frozen, so maybe not the most efficient hail growth in getting lots of that supercooled liquid water up to grow these hailstones. On the right, we see a much different story. We see some of these higher values of ZDR, possibly telling us we are getting more liquid water up there to really produce some of these larger hailstones. And it's also pretty noisy. Look at the variations in the ZDR values throughout the region where we'd be looking for hail growth. That tells us maybe we're starting to get some of these large, really large hailstones like this size with liquid water growing on them, some really strong hail growth going on. So moving on next to correlation coefficient, CC, for those in the academic world, ρHV. And what we're looking at here is, values pretty close to 1 for the most part throughout the area where we'd be looking at the growing hail. That tells us things are pretty uniform. CC values close to 1 mean we're looking at a pretty uniform volume. There isn't much diversity in the types of precipitation, the shapes of the precipitation. And as you see here, these hailstones look all pretty, spherical, relatively speaking, to our one on the right. And so that's telling us, 1, it's mostly ice, and 2, there isn't huge variations in the shapes of the particles we're looking at. We go to the right, huge differences. Our CC values are much lower. We see values below 0.8, even a few pixels below 0.8, mostly below 0.9, but that's still a significant drop-off. It's telling us 3 things. 1, there's likely a good mixture of liquid and ice, so again, that's what we want to see for really big hail growth. 2, that we're likely dealing with a diversity of shapes. Look at this guy again. You can tell that's probably going on. And 3, some of these hailstones are getting so big they're actually kind of messing with the radar signal. And they're getting to these sizes of really 2-inch plus in diameter that they're also reducing correlation coefficient. So big signal right here in CC that we have some large hail forming, very large hail forming. Lastly, we look at specific differential phase, a great dual pole variable to show us where there's liquid water. When values are close to zero, it tells us really there's not much liquid water. And sure enough, we're looking here again where we were most interested in hail growth, and values are pretty close to zero. So again, we don't really have lots of liquid water to help grow really, really big hailstones. On the right, though, in our hail growth zone, look at these values, much higher. Again, likely telling us that, one, we have a good amount of liquid water present to sustain giant hail growth, and two, the noisiness of the specific differential phase is also telling us likely some of these hailstones maybe are getting to really big sizes where they're affecting the radar signal to create this kind of noisy character to a specific differential phase. So those were some of the context clues you can look at. You want to look to that hail growth zone where they're forming aloft to really get the best idea of the size of hailstones forming. By the time they're reaching the surface, as they're melting, you're getting interference maybe from ground clutter, so on and so forth. It's a little bit tougher to tell. Sometimes one storm can masquerade a little bit like another one. Maybe reflectivity is really high, but it's a lot of smaller melting hail. So when you look up in the hail growth zone, you can see where those hailstones are forming, and you can get the best idea of what size of hail seems to be forming. And this was a great example. All these prolific hail producers recently, we were really able to see, when you look aloft in the hail growth zone, which ones truly have the best potential to produce giant hail. So thanks for watching this. Hopefully we'll have time to do more little case studies and case reviews like this going forward in the future.